Okay, we're recording. So here's the next example that we're going to talk about. So we are going to try to do the following integral. Here it is. This integral in the xy plane. Specifically, notice that our domain for this integral is this region right here, defined in kind of a weird way. This region is defined by its being between these two curves. Have these two equations, and let's see here, color choices. These two curves that have these two equations like that. So kind of a weird setup, and I'll note that this seems pretty manufactured. I mean, what are the odds? How would this ever come up naturally? Well, believe it or not, this comes up really naturally. In fact, this is a slightly cleaned up, streamlined version of a very real circumstance that I first encountered in a thermodynamics class in my past life as a second major in physics. Y'all, or those of you who are engineers, will probably at some point take a thermodynamics class. I think you'll probably see this same setup. Again, this is a slightly cleaned up, streamlined version of it when you study something called the Carnot cycle, aka the Carnot engine, which is an important construction in thermodynamics. So anyway, very real world, believe it or not. So what a horrible domain. Let's take a moment to appreciate that. Right? There's corners, and so when you slice this, whichever way you slice, either vertically or horizontally, whatever, you're going to hit two corners. So we're going to have three separate things to deal with here, whichever way you slice it. Nobody wants that. Okay. There's a particularly clever move for dealing with this situation, and that is as follows. First thing, make sure that your equations are written as level sets. Stuff equals constant. Turns out to be a really handy move. We'll see why in a moment. Next, look at what functions you're taking level sets of and call them u and v. So for example, xy, I'm going to call that u. Xy squared, I'm going to call that v. Okay, having done so, notice that what you have is a change of variables function. You have two variables, u and v, as functions of two other variables, x and y. And so it's a change of variables function. The only problem is it's going to the left instead of to the right. We weren't really hoping for that. We're hoping the pullback will go to the left. So we were kind of probably expecting that the function would go to the right per all that stuff we talked about pullbacks. Going backwards through the function. So we're going to have to figure out how to deal with that. Luckily, of course, what we ended our last class with does directly address at least part of this scenario. And that is that if you look at these two functions that are inverses of each other, right, then the stretching factors are reciprocals of each other. And again, quick reminder, this looks at a glance to be an immediate consequence of the algebra of fractions. At a glance, it looks like you're taking a reciprocal of a fraction, and the denominator becomes the numerator and all that business. Of course, that is absolutely not what is happening. Don't forget, this is not a fraction. It's a determinant. Right? And we write it as a fraction because in certain ways it behaves like a fraction. And I'll say what we have here, this is not a consequence of the algebra of fractions, but we write this thing as a fraction because it behaves like a fraction even though it isn't. So yet another motivation, yet another thing that I like about this notation. Okay, anyway, back to here. We know how to deal with the fact that this function's going the wrong way. So, cool. Let's just proceed. Alrighty. So, let's look at these curves again. Let's see here. We'll look again at these two curves here. These two curves like that. Now, what do they look like when you look over into the UV plane? Well, keep in mind, if xy equals various constants, but if xy is now equal to u, that means that in the UV plane, they become u equals various constants. Namely, they're just straight vertical lines, and you gotta love that. And then likewise, these curves over, let's see here, colors. These two curves over here, right? I didn't highlight those well, but these two curves circled in red with the xy squared equals various constants. Well, that means v equals various constants. That gives me horizontal lines. There we go. So the pullback domain very conveniently becomes just a rectangle. Is everybody with me? Okay. All right. Now, real quick, let me make a plug for why it's important, as I previously claimed. If I can get these things to erase. Here we go. Why is it important that we set these things equal to constants before we started doing business, before we set up our change of variables function? Well, notice those are what we end up with u and v equaling to. And I sure do like it when u and v equals constants, because then I get a rectangle, right? So it just happens to work out that if you set up your equations as level sets, it is because of that your new domain will be a rectangle, and that's why we do it. Okay. Alrighty. So, proceeding along. Let's compute a stretching factor. Now, sadly, we only have u and v as functions of x and y. I'm going to try to avoid, in doing this example, I'm going to try to avoid solving for x and y. If you can solve for x and y, then I suppose you could, and that'd be a perfectly reasonable way to do the question, but then we're back to basically all the examples that we've seen before of this sort of thing. We've already seen a bunch of examples of that, so there'd be kind of no point in me solving for x and y. I want to show you how to proceed, though. If you don't want to or can't, whatever the case may be, solve for x and y. So I'm going to leave it as that we have u and v as functions of x and y, and let's just pretend that we can't go the other way. So I can't take the derivatives of x and y, I can only take the derivatives of u and v. So I'm going to compute partial uv, partial xy. Easy algebra, you take a couple of partial derivatives, write down the determinant, you multiply it out, etc., and out comes xy squared as my stretching factor. But again, specifically, this is that stretching factor right there. Okay, what are we going to do with that stretching factor? Is this the one that I need? Or, let's see, I'm going the wrong way. It's backwards. Do I need to take a reciprocal? Let me momentarily skip over that question. Let's just remind ourselves what we're doing. Here's the integral that I was asked to compute. So here's the differential that I need to rewrite. I want my integral to end up being a du dv integral. So I want this dx dy to end up being something times du dv. So I ask now, what should I multiply by du dv to get dx dy? In other words, what is dx dy equal to in terms of u and v? Right? Well, again, this is bogus and cringy, but will always lead you in the correct direction. That cancellation is the way that I would like to do it. Always put in here as the stretching factor that you want to multiply the thing that makes the cancellation go the way that it sort of should go. And then notice, as desired, we get dx dy kind of suggested by what's left over after the, again, fake cancellation. So this nonsense will always take you the correct direction. So it's very convenient nonsense. All right. So from the point of view of that nonsense, apparently the thing that we need is partial xy, partial uv. And now I'm going to come back up to where we were. Oh gosh, let's see here. This doesn't quite all fit, so we'll do it like this. I have partial uv, partial xy. I want partial xy, partial uv. And so apparently, in order to get this thing that I want, I'm going to have to take a reciprocal. Everybody see how that plays out? Everybody see my rationale there? Okay. All right. Okay. So, convenient, let's see here. And that means that this thing, with the reciprocal having been done, 1 over xy squared, that's my relevant stretching factor. That's the one that I actually needed. And now, don't forget, of course, we obviously the integrand still there. And so all together, my new actual integrand with the stretching factor included and everything becomes this. And here we go. I have a new integral, du dv. Notice the new bounds, right? So my integral is in the uv plane. So my domain has been pulled back. I'm on this domain here, rectangular domain, constant bounds, therefore. So gotta love those constant bounds for u and v. Okay, yes?
How often do we have to split the stretching factor?
That's a good question. I mean, I don't know how to quantify that exactly. It's not rare. So there's a lot of weird circumstances that to which we apply change of variables, and it's not unusual for your change of variable. You know, for the relationship that you have, the most easy relationship to write down between the u's and v's and the x's and y's or whatever your variables are for the circumstance. Yeah, it really could go either way, and I don't know how to quantify how often. It probably depends a lot on the context. I wouldn't be surprised if it's more so in one field of engineering, less so in a different field. Yeah. So it's not, that doesn't really answer your question, but I basically can't answer the question. Okay. All right. Now we're not quite done. Do notice I've got a UV integral, and yet my integrand not in terms of u and v. This does seem to kind of slightly defeat my goal. My goal was to not have to solve for x and y, right? Notice I didn't want to have to invert this function. I didn't want to have to solve for x and y. And here I am. Well, golly, kind of at a glance looks like I might need to solve for x and y. Importantly though, I don't. All I need to do is solve for x to the 7th times y. X and Y specifically, I don't need. Sometimes that might actually be easier, depending on the circumstance. Anyway. In this case, I'm going to show you how this plays out, and I want to emphasize how you do this, how you rewrite your new integrand in terms of u and v is going to be different for every example. It depends on the nature of your change of variables function and the nature of your integrand. But this is a broad stroke kind of strategy that you can kind of follow. Here we go. This is the thing that I need, x to the 7th times y. And notice here's what I have. I already have that u and v are those formulas. So what I have and what I want are both products of powers of x and y. So now I ask rhetorically, strategically, what should I do to these products of powers of x and y to produce this product of powers of x and y? Yeah. Did you have a question? No. Oh, okay. All right. So I have these products of powers of x and y. I want this product of powers, and I'm going to propose that being as they are products of powers, maybe I should take a product of powers of my products of powers to produce this other product of powers. Because after all, when you take a product of powers of products of powers, algebra being what it is, you get a product of powers. Seems like a reasonable candidate. Now, so what I've got in purple here, that purple part is, again, tailored to this circumstance. Right? Given what the green is, given what the blue is, the purple seems like a reasonable guess. Doesn't look like it's going to involve any trig. It's just not how the algebraic players here I don't know, it just seems like a reasonable guess. So in other examples, yeah, everything's going to be different. You'll make a different guess for the form of this relationship. Always different for every example. That said, you can multiply this all out. Notice then that leaves me needing a plus b to equal to 7. And I further need a plus 2b equal to 1. So if I want this to work, then I need for this system to work, and so I need to solve that system, and that's just a little bit of Math 218 linear algebra, and there you go. Yes?
So
yeah.
When we split it, so the splitting up of x and y, was that arbitrary?
The what now?
Splitting up of x and y into that product.
I'm not following.
Like the x, when we went from x to the 7.
This?
Yes. To xy to the a.
This?
Was that split up arbitrary?
No. This is my integrand, so that's what I really need to understand, right? And these things here, what I'm calling u and v, are literally the change of variables function that I already set up, right, in order to make my domain work out well. So this is basically, like I was saying, this is what I have and what I want already arranged. And so what remains then is to try to figure out, well, what's the relationship between them? And that's why, because they're products of powers, I guess this form. Yeah. All right. Okay. So, now once you know A and B, then it's all over but the shouting. That tells you specifically then that this, keep in mind what my integrand was is what we're talking about. And so my integrand is now this function here of u and v, and now it's all over but some easy integration, and we win. Okay. All right. So, we have several successful wins under our belt for change of variables. And I want to remind y'all that when we first started talking about change of variables, I skipped over some details. I made the observation, and we've got a lot going on as it is. Let's focus on the mechanics of how to do change of variables, and let's get some wins under our belt, and then we'll go back and worry about some details that at the time I didn't want to get bogged down in. And specifically, where does this formula for the stretching factor come from? Right? I made this claim that the stretching factor is the absolute value of the determinant of the derivative matrix. I just pulled that out of thin air. So why does that work? Okay, well here's the reason. And I want to remind you what the stretching factor's job is to be something that you multiply by a little piece of input area, du dv. What do you multiply that by to get the corresponding piece of output area, whatever that is? Right? So, okay, well, I've got the rectangle on the left, I've got this parallelogram on the right, and I want to know what is the area proportion between these two things. So, the way I'm going to study this is I'm going to view these edges as vectors. So, this edge here I want to view as a vector. I want to think of that as representing a displacement or a change from one place that I might be in the domain to a nearby but different place in the domain. So this vector, viewing this as a vector, allows me to view this edge as a change. And then there's this corresponding edge over here on the right. Also, I'm going to view as a vector, viewing it as then the change as I move along that edge of the parallelogram. And so what I've got, if you think about it then, I've got an input change and I've got an output change. And how do I relate input changes and output changes? The derivative matrix. So the derivative matrix is literally then what I multiply by my input vector to get my output vector. And I think it's a pretty easy pitch that this input vector, let me focus on this input vector, notice it's in the E1 direction. It's horizontal. That's in the E1 direction. Its magnitude is du because it represents a width of du. So as a vector then, this is E1 du. And that makes this vector dg times E1 du. Everybody on board? Okay. All right. So, cool. I know this vector is this thing, which has this formula. And let's see here. Analogously, this vector has this formula. And I'm going to cite an old fact from chapter 1, and that is that if you want to compute the area of a parallelogram is the absolute value of the determinant of the matrix that you get when you make those edges the columns. Everybody remember that from chapter 1? That was a long time ago. All right. Okay, so we're in business. We're doing algebra at this point. And what am I going to do with this algebra? Well, a couple of conveniences come up. First of all, this du right here, I point out is a scalar. It's a scalar factor in this entire column. Flashback to Math 218. If you have a common scalar factor in an entire column in a determinant, you can just factor out that common factor. And then likewise, this dv also, that's a common factor in this entire column. So I can factor that right on out as well. Okay. And that leaves me with just this matrix to understand. And this looks like a lot. It looks weird. Turns out this is actually really simple. You just have to look at it just the right way. Let's take this matrix here one column at a time. What can I say about this first column? Okay, well, let's see here. That first column. Now, forget where this first column came from. Forget about everything else on the page. Let's just look just inside of this green circle here. What I see in here is I've got a matrix times a standard basis vector. And this is one of my favorite facts about matrices. When you multiply a matrix times a standard basis vector, you get the corresponding column of that matrix. So this then is literally the first column of DG, and I'm going to go ahead and write that down. So the first column of the orange matrix, whatever that weirdo orange matrix is, its first column is the first column of DG. Likewise, and morally equivalent reasons, this second column of this orange matrix is the second column of DG. So now let's just step back now and think about the whole thing. This orange matrix, its first column is the first column of DG. Its second column is the second column of DG. It's got the same first column as DG. It's got the same second column of DG as DG. It's DG. Right? So that's you got to kind of let that sink in for a second. But this whole orange matrix here is nothing more than DG. So really neat fact, using properties of linear algebra. All right. Okay, and that gives us the win that we were looking for. After all, notice what we have now written is that this area here relates to this area here by way of what I previously claimed to be the stretching factor. What I have in purple here is what you multiply by the green area to get the blue area, and so it's our stretching factor, and again, as previously claimed, absolute value of the determinant of the derivative. So, is everybody all right with that? You can see why I skipped this at the time, right? There's a fair amount of discussion that goes into this, and there was a lot going on when we were just trying to get the mechanics, the mere mechanics of change of variables down. So this is, I think, a good thing to postpone. Okay. All right. Now, here's another thing that I kind of blew off previously. What if you're in 3 dimensions? Right? We were strictly 2 dimensions when we first approached this. I'm going to point out in 3 dimensions, it's morally the same thing. If you have a nice volume, not area, and if you apply a change of variables function, thus giving you a weirder volume, and if you somehow, and again, not rare, if you find yourself doing a triple integral over that image volume as your domain. then strategically we can just say, hey, let's do a pullback. Let's take that integral on the right, rewrite everything by plugging in, rewrite everything in terms of the variables on the left, then having an integral defined on this green pullback region on the left. And this pullback region, of course, is much more desirable. After all, it's a rectangular box. We're going to have constant bounds, much, much, much better. And this is same basic idea. In other words, the strategy is the same. And all you have to do to make this work is figure out what the corresponding stretching factor is. How much does this function stretch out volumes this time? And that stretching factor is, again, the absolute value of the determinant of the derivative matrix. And I'm going to leave that particular detail to be an exercise for y'all. This is a very healthy exercise. It's going to be an argument practically identical to this. The only difference is that it'll be instead of a rectangle, it'll be a rectangular box. Instead of a parallelogram on the right, you'll have a parallelepiped. Instead of a area that you're computing, it'll be a volume. And of course, how do we compute a volume in 3 dimensions? Well, a volume in 3 dimensions, parallelepiped, again, it's the absolute value of a determinant and then of a appropriate corresponding matrix. And that's where the details start to differ a little bit, but you're just going to end up with a very, very similar calculation, and I claim you end up with this same result. Again, healthy exercise. I hope you'll take a whack at it. If you get stuck, confused, not how to get started, don't know how to proceed at a certain point, come on into office hours. I'll be very happy to talk you through it. Okay. All right. Okay, so I'm going to show you an example of how to use, and real quick, also analogous notation for the Jacobian determinant. Partial kind of, shorthand, fake fraction, notation. Again, very handy. Again, how nice is this? The following nonsense, right? It's like the UVWs cancel, which of course they did not, but it's like they did, thus giving you XYZ volume. So having it look correct in this nonsensical argument will always have you pointed the right direction. Okay. All right. Okay, real quick lemma before we go on. Neat fact about linear transformations. Almost seems too good to be true, but if you have a linear transformation, the matrix that represents the transformation, that same matrix is also the derivative matrix for the transformation. Seems a little too weird to be true. But it turns out easy to check. Super easy to check. And again, this is another one I want you all to take a few minutes to actually crank out. All you're going to do is presume that you have a matrix, let's say, for example, A, B, C, D, E, F, G, H, I. Just take a for example matrix, write down the corresponding linear transformation, compute its derivative matrix by taking the appropriate partials, and what you're going to find is that sure enough, you get the A matrix, this exact same A matrix that you started with. So it's just a matter of writing that all down and confirming that indeed it works. Okay. All right. So again, good exercise. Let me know if you get any troubles. Come to office hours. Happy to help. Okay. So with that noted, here's the big example for 3-dimensional change of variables. Let's suppose that we're looking at this parallelepiped in the XY plane, the XYZ space as my domain for this triple integral. How would I compute this triple integral? And let's take a quick moment to recognize what a nightmare of a question, right? You look at this domain, and at a glance, it doesn't look that bad, right? It's got flat faces and everything. It seems pretty innocent. But there's 8 vertices, 8 corners, you might say. Only 2 of which are first and last. as you slice. That means that in the middle, as you're slicing this thing up, you're going to have 6 corners that you're going to be slicing through, which means that you'll have 7 separate iterated integrals created just by that outside slicing. And then here's where it gets worse. Each one of the slices also full of corners. And I don't know if you've thought through the geometry of parallelepipeds very much, but just think about a cube. You can take any box, like take a recent Amazon delivery or something. Take your box and just stand it up on its corner or something, right? And then think about the various slices and what they look like. Some of them could be as complex as hexagons. So you're going to have multiple corner hits on each of multiple regions as you slice through this process. You could have dozens of iterated integrals come out of this. It could be super ugly. It's a nightmare. It's basically intractable as written. Is that cool? Everybody see what I'm talking about here? It's a nightmare of a question. Nobody wants that. Okay, here's the slick move. Very clever idea. I wish I thought of it. Let's see here. Okay, so these vectors that are the edge vectors for your parallelepiped. Slick move. Make those the columns of a matrix. And use that matrix to define your linear transformation. That's it. It's very easy to state. Whatever the edge vectors are, again, in this case, they're given. Defining your parallelepiped, let that be the columns of your matrix that defines a linear transformation. This then is your change of variables function. And what's beautiful about this is that then your parallelepiped is literally the image of this unit cube over here. And when we do a pullback, right, we started with this horrifying, terrible domain on the right, and notice pulling back then to the unit cube. Well, the unit cube, you just couldn't get any better. As a domain for a triple integral, constant bounds, zeros and ones, I don't know anything nicer than the unit cube. So, massive victory. Right? If we can make this all work, right? If we can do this pullback, huge win. Let me pause before I go on. Does everybody see why we want to do this? How nice it is? How we're getting away from the horror story on the right-hand side? Okay. All right. Let me persuade you before I go on this claim that the image of the unit cube truly is this parallelepiped. That's an easy observation about standard basis vectors. So, taking, for example, this first standard basis vector over here in the UVW space. What's the image of that first standard basis vector? Well, I'm going to multiply that standard basis vector by my matrix, the matrix representing my chosen transformation. And when I multiply a standard basis vector times a matrix, I get the first column, which by construction, this first column is the first edge of my parallelepiped. So by construction, basically, first edge of the cube goes to the first edge of the parallelepiped. And then likewise, second to second, third to third, and therefore cube to parallelepiped. Works out really, really nicely. Okay. All right. Mostly over at this point with just some details to plug in. I've, of course, got to rewrite my dx, dy, dz. Again, the faux cancellation leads me to understanding that this is the stretching factor that I need to do. So I'm going to need to take partials of x, y, and z with respect to u, v, and w. Now that's just a matter of writing down the linear transformation, taking the various partials, etc., etc. Oh, wait, we already know that if you have a matrix representing a linear transformation, it is immediately the derivative matrix for that transformation. So we don't even have to compute the derivative matrix. We have a theorem that tells us the derivative transformation. So, boom, I instantly know that this is my derivative matrix, and so that's what I need to take the determinant of. Everybody all right? Okay. And one last little detail. This is, a minor little detail, but I got to figure out now, what do I do with this z? How do I rewrite z? How do I plug in for z? And remember, again, a broad stroke fact when you're doing change of variables, when you're doing pullbacks, the change of variables function tells you how to plug in. So in particular then, let's look at, here's my formula for my change of variables function. Let me write this down. This says that my A matrix times UVW is XYZ. Oh man, let me try that again. XYZ. There we go. And let's see here. Apparently it says Z. Z is what I need. Okay. Well, there's Z in my formula for my change of variables. And so I just want the last row of A dot UVW, and that then gives me this right here. Notice I'm just queuing off of that last row, 015.UVW, and that formula is my Z. How we doing? Everybody see how that all fits together? So, three-dimensional change of variables. I mean, yeah, the picture's weirder. There's 3x3s instead of 2x2s, but structurally the argument's the same, right? And there's just kind of different annoyances to deal with. But arguably also, there's a lot more value because, when we were talking about two-dimensional change of variables, we were, bemoaning that, we might have to chop it up into 3 pieces. Right? This would be dozens of pieces. So, massive victory, massive streamlining. By turning that into just a single integral. Okay. All right. Okay, so moving along. I want to remind y'all, Section 5.5 is a monster. It's huge. We are now about, probably a little over a third of the way through Section 5.5. It's just huge. Anyway, proceeding along, this next section of Section 5.5 is about how to apply change of variables to a certain circumstance that comes up extremely often, that makes this arguably the most common usage of change of variables is to a very particular small set of change of variables functions. And here they are. They are the coordinate system functions that we saw back in Chapter 1. And now y'all may have thought at the time that it seems like a weird choice. You may recall I suggested that it was natural to think of polar coordinates as being a function from the r theta plane to the xy plane. Seems a little unnecessarily heavy-handed. But now I can, with that having been noted, I can just say, hey, yeah, well, check it out. I have a function with 2 inputs and 2 outputs. How about that? That is a change of variables function. I can just choose to use that as a change of variables function. Likewise, cylindrical coordinates. Seemed a little weird to think of it as a function, perhaps, but now that I understand it as a function, I can say, oh yeah, look at that, it's 3 in, 3 out. I'm going to choose to view that as a change of variables function. And ditto spherical coordinates. Change of variables function from R3 to R3. Okay, so now all we got to do is compute some stretching factors, and off we go. So various partials to be taken, assembled into a matrix as usual. Take the determinant as usual and simplify. Yada yada yada. By the way, this is something that everybody has to do once in their lives. I have done mine. It's your turn. It's not that bad. This will take you 30 seconds. No big deal. Easy partials. Make a matrix. Easy determinant. And then one observation of the Pythagorean identity, and you'll find that the Jacobian determinant is just R. Very handy fact. Every time that you use polar coordinates as a change of variables function, which is a lot, every single time the Jacobian determinant is always just R. So this is not only a good calculation to have done, it's a good calculation to remember the result of, because we will be regularly using polar coordinates as a change of variables function, and knowing the stretching factor, knowing the Jacobian determinant is R is super valuable. Okay, ditto for these others. A little bit more effort here. This is 3 by 3, but there's some zeros involved, and it's not that bad of a calculation. Again, ends up being R. Again, no surprise. We know cylindrical coordinates is pretty much polar coordinates. Just, also Z. So it's no surprise you get the same stretching factor, hopefully. Okay, spherical coordinates. Now this one is more tedious. You take the appropriate partials here, and you assemble them into a 3 by 3 matrix. Yeah, it's pretty big and ugly. And then when you write out the determinant, yeah, it's pretty ugly. But the Pythagorean identity kicks in several times. It simplifies massively. And again, this is something everyone should do once in their lives. And again, it's not that bad, but this one will absolutely take you more than 30 seconds. This is at least, 5 minutes, something like that, depending on how fast you move algebraically. But I think, again, everyone should do this once in their lives. Give it a shot. It's not that bad. But it's a healthy exercise, and nice, simple, compact, convenient answer. Rho squared sine phi. All right? So again, healthy exercise. Give that a try. Okay. All right. Now, here's the bad news. The bad news is that Jacobian determinants are not the stretching factor. The stretching factor, tragically, is the absolute value of that Jacobian determinant. So I really actually need to be taking the absolute value of R, and oh my gosh, does that mean that every time I want to use this change of variables function, which again I claim is going to be a lot, every time do I have to put absolute value of R? Oh my God, I hate absolute values. Because you always have to break it up. Then, we'll have one side of the integral where the thing is positive and the other side where it's negative. What a drag, right? So do I have to actually keep those absolute values? Well, kind of, yeah. Unless you cleverly arrange for the thing on the inside to always be non-negative. How could we arrange for R, this thing on the inside, always to be non-negative? Answer, just make a promise that you will always choose your polar coordinates with R to be positive. And that's a choice that you can choose to make for yourself, right? At any point, there's multiple polar coordinates for any given point, and you got this theta or that theta, and just always choose polar coordinates so that your R's are always positive. And if you do this, then you're always taking the absolute value of something that's never negative, and so then your stretching factor truly does simplify just to R. So that's the big heads up. It's not that you have to make these clever choices, right? If you want to make your life hard for yourself, you, I suppose, can. I just don't see why anyone would ever want to do that, right? So please always choose your polar coordinates to be positive, well, more to the point, non-negative. And then you don't have to worry about absolute values. Your stretching factors just are. Life is good. Okay. Okay, very similarly, of course, for cylindrical coordinates, just, there's lots of different cylindrical coordinates, lots of different choices you could make. Just always choose the one where r is positive. And then you're taking the absolute value of positive, which is just the thing. It's whatever it is. And so, again, you get to throw away the absolute values. Okay. For spherical coordinates, a little different. A lot of people mistakenly think that, rho is kind of like r, and so I guess the analogous requirement would be for rho to always be positive. But here's the thing. Look at your rho here. What benefit do you get if you insist and promise, I promise I'll always choose rho to be positive? Does that make the expression on the inside of the absolute value always positive? Nonsense, not even close. In fact, it doesn't make any difference at all. That rho is going to get squared. So who cares? It's not about rho. This is a very common misunderstanding. A lot of students, again, they think rho is kind of like r, and so, it's probably rho. It just isn't. Right? What we really need to worry about when we're doing spherical coordinates, oh man, I need to get a new stylus. I've got to worry about sine phi. I need to make some choice that will always, for sure, 100% guarantee, make sine phi non-negative. And now, again, that's easily arranged. This is the choice I need to make. And again, I emphasize choice. You do not legally have to do this. You can do it the hard way, I suppose, if you want. I just can't imagine why anyone would want to. So choose phi always to be between 0 and pi. And that will make sine phi non-negative, and then rho squared sine phi is non-negative, and then the absolute values dissolve into irrelevance. And again, don't have to worry about them. So big wins there. So here's the really, really good news. These values of phi that you really have to make sure that you always choose, these are everybody's favorite values of phi anyway. Right? They're the obvious ones, the ones that are geometrically most visible. So promise that you will always make the easiest choices of phi, and then good news, you also get the convenience of being able to ignore the absolute values. Okay. All right. So, let's see an example. Let's look at this domain right here, first quadrant portion of the unit disk. I want to note that this is an annoying domain. It's not that bad, I suppose. Could be worse. But let's see how it works out for this integral right here. X squared plus y squared. And by the way, this little bit of notes down here, I just added at lunchtime today. So if you haven't very recently downloaded the notes, then you won't see this. I did upload them though to the Sakai site, so you can download at your convenience, and I encourage you to do so. All it is an observation that this integral, if you slice dy dx, namely dx on the outside, and check your bounds and blah, 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 y is a function of x, etc., what you will find is that this integral turns into this, and this is undesirable because square root in the bounds. Right? Because we had to solve for y as a function of x, and well, on this curve, y as a function of x has a square root in it. And this square root on these bounds, you can think it through when you start doing, inside-out calculations. When you do your dy anti-partial, you're going to get odd powers of y, which means you're going to have odd powers of a square root. And so you're going to end up with a polynomial times the square root, and that's no fun at all, right? And it can be done. It can be dealt with. You can do really clever integration by parts and possibly trig substitutions, or there's some clever moves that you can pull, but it's effort for sure. So nobody wants to do it this way. This is highly undesirable. Okay, so let's look at the alternative. Let's use polar coordinates as a change of variables function. And doing so, this edge, theta equals 0, r goes from 0 to 1, becomes that edge. This edge, that's r equals 1, theta goes from 0 to pi over 2, that's this. Let's see here, this edge here, theta equals pi over 2, r goes from 0 to 1, is like that. And then, let's see here, this edge here, if you think this is the weird one, this edge on the left, that edge is where r equals 0. So this entire edge over here goes down to just the origin where r equals 0. But the nice punchline then is this entire rectangle on the inside has as its image this quarter disk, and we have ourselves a pullback domain. And I'm out of time, so we're going to have to finish this next time. But you can see what's going to happen is that this integral here on that domain is going to pull back to this integral over here. We'll talk through the details next time. More important point, though, is that it's on a rectangular pullback domain. This is a nice win. We get to avoid all of these ugly square roots, polynomials, all this nastiness on this blue integral. We're going to have an integral on a rectangular domain in the r theta plane with constant bounds. Life is good. So polar coordinates as a change of variables. Big win. Drawing the line right here, we'll pick up here on Wednesday. Y'all have a good day. See you later. Don't forget to make sure I mark you down for attendance.